Children, once again welcome to our physics class. Hope you all are fine over there. Children, in the previous session we had discussed about longitudinal waves and transverse waves. We just went through the introductory concepts of the chapter waves. Today let's discuss about waves in detail. So let's get started with today's session. So today we are going to discuss about displacement in a progressive wave. So amplitude and phase together describe the complete displacement of the wave. Displacement function is periodic in space and time. Displacement of the particles in a medium takes place along the y-axis. Generally, displacement is denoted as a function of x and t, but here it is denoted by y. So displacement, you know the concept of displacement, that is the change in position of the particles, that is displacement. So in the case of a progressive wave means traveling wave, amplitude and phase together describe the displacement of the wave, and we will discuss about amplitude and phase in our coming sessions. So in the case of transverse wave, displacement is given as y of xt. Okay, so displacement is represented as y of xt. That means y is a function of x and t, where x is the propagation of the wave along x-axis. So x denotes wave is propagating along x-axis and the particles oscillates along y-axis. Okay, so particle oscillates along y-axis, wave is propagating along x-axis. That means it is a transverse wave because the particle oscillates perpendicular to the propagation of wave. Hence, we can write such wave as, or such wave can be represented as y of xt is equal to a sin kx minus omega t plus phi. This is the expression for displacement of a progressive wave, or simply a progressive wave can be represented by this expression y of xt is equal to a sin kx minus omega t plus phi. So, this expression is very important. You must always remember this expression. So, a progressive wave can be represented by this expression y of xt is equal to a sin kx minus omega t plus phi, where a is the amplitude of the wave and x denotes wave is traveling along x direction, and phi is the phase angle, initial phase angle of the wave. Okay, so this is the expression for displacement, and this expression is same as the displacement equation which is used in oscillatory motion. So we will study about oscillation later. And similarly, we can represent the displacement as a cosine function also. So we can represent y of xt equal to b cos kx minus omega t plus phi. Okay, so as both sine and cosine functions, we can also represent a wave as both sine and cosine function like this. Then y of xt is equal to a sin kx minus omega t plus phi plus b cos kx minus omega t plus phi. So these are the different ways to express or to represent a wave. Okay, so anyway, this is the expression for a progressive wave, a sin kx minus omega t plus phi, where a is the amplitude of the wave, k is a constant which is known as wave number or propagation constant. So k is a constant called wave number or propagation constant, and omega is the angular frequency, and phi is the initial phase of the wave. We will discuss about phase in our coming session. And the terms in the bracket together constitute phase, kx minus omega t plus phi. This term which is in the bracket is phase of the wave. Now let's discuss about each component of that wave expression one by one. So amplitude. Amplitude and phase together describes the position of the particle. That means amplitude and phase helps us to understand where is that particle in a wave. Amplitude is the maximum displacement of elements of the medium from their equilibrium position as wave passes through them. Okay, and you had already studied about amplitude in your class 9 physics. So this is the maximum displacement of the particle from its mean position or equilibrium position. Amplitude is denoted by capital A. And if you consider a transverse wave, here the distance between the point P and Q, this distance PQ, is the maximum displacement. Hence, this maximum displacement of the particle is known as amplitude. Okay. Now, what do you mean by phase? Phase of a wave describes the state of motion as the wave sweeps through an element at a particular position. Okay, so phase represents or describes the state of motion as the wave sweeps through an element at a particular position. Okay, so here A, B, C, D, E and certain points are plotted on the wave. And if you want to determine the phase of the different points on the wave, how can we determine the phase? Okay, so in phase, when will you say that two points are in phase with each other? So two points are said to be in phase with each other when these 2 points are at the same position and they both are doing the same thing. That means both the 2 points are exhibiting the same behavior. So here when you consider the point B and when you consider this point, that is F, this point is F, this peak point is F. So both B and F are in same phase with each other. Okay, why? Because both are in the same position. But B and D are not in same phase with each other. And what do you mean by out of phase? Out of phase means they are at the, even though they are at the same points, but they are doing opposite thing. So if we consider B and D, they are at the peak of the wave, but in B is at the peak point of the wave, but D is in the valley point of the wave. So they are doing the opposite thing. So both the points are exhibiting the different behavior. So out of phase means which is not in phase. Now expression for phase. What is the expression for phase? So I had told you this is the expression, general expression for a wave. So we can consider this expression as the wave equation also. Y of xt is equal to a sin kx minus omega t plus phi. Here A is the amplitude and the terms inside the bracket, that means kx minus omega t plus phi is the phase. And where is the k is the wave number, x is the displacement of wave along x direction, omega is the angular frequency, t is the time, phi is the initial phase angle. And what is wavelength? The term wavelength means length of the wave. Simply we can consider wavelength as length of the wave. And wavelength is defined as the minimum distance between two consecutive points in the same phase of wave motion. That means it can be the distance between any two consecutive crests, or it can be the distance between any two consecutive troughs, or it can be simply considered as the length of one complete wave. That is wavelength. It is denoted by lambda. In case of transverse wave, we use the term crest or peak of the maximum displacement, and the point of minimum displacement is known as trough. In case of transverse wave, wavelength is the distance between two consecutive crests or the distance between two consecutive trough. In case of longitudinal wave, wavelength is the distance between two compressions or the distance between two rarefactions, provided the compressions or rarefactions are nearest. So you know, transverse wave propagate as crest or trough, but longitudinal waves propagate in the form of compressions or rarefactions. So the distance between any two consecutive compressions or consecutive rarefactions can also be considered as wavelength in the case of longitudinal wave. Now what is wave number? So in the wave equation you had already seen this term k. So k is known as wave number or propagation constant, and this wave number describes the number of wavelength per unit distance. So in a particular distance, how much wavelengths have covered, that is denoted by k. Okay, and it is a propagation constant because it tells us about the propagation of the wave, and it is an indirect way of describing the propagation of a wave. Now let's be familiar with some parameters in a wave, that is time, period, frequency, angular frequency, like that. So what do you mean by time period of a wave? Time period of a wave is the time taken through one complete oscillation. That means time taken to complete one wave. That is time period, and it is denoted by capital T. And frequency of the wave is defined as number of oscillations per unit time, and it is denoted by nu. Okay, it's not V, it's nu. So frequency nu is the reciprocal of time period, and it is 1 by capital T. And angular frequency. Angular frequency, you know, it is the frequency of the wave in terms of a circular motion, and it is denoted by omega. Okay, and what is the angular frequency expression? Angular frequency, omega is equal to 2 pi by T. And in terms of linear velocity, angular velocity is equal to, not linear velocity, sorry, frequency. Angular velocity omega is equal to 2 pi nu. Okay, so angular velocity omega equal to 2 pi nu, where nu is the frequency, or angular velocity omega equal to 2 pi by T, where T is the time period. Traveling waves. So what do you mean by traveling waves? Traveling waves are those waves which travel from one medium to another. They are also known as progressive wave because they progress from one point to another. Both longitudinal and transverse waves can be traveling wave because both can propagate from one point to another. Wave as a whole moves along one direction. Now let's derive an expression for the speed of a traveling wave. Now for that, consider this particular figure. So in the figure you can see a wave. Okay, and this wave is propagating along x direction, isn't it? And it is represented by y is equal to a sine kx minus omega t plus phi. Because we had already studied about the expression for a wave traveling along x direction. And what is that expression? It is y is equal to a sine kx minus omega t plus phi. Okay, this is the wave equation. Now, as the wave moves, each point on the wave retains its displacement. This is possible only if kx minus omega t is a constant. Okay, so as the wave moves, each point on the wave retains its displacement. That means here you can see as the wave advances, first the point A was here, and after a time t, the point A has reached here. And what is the displacement taken place? It is delta x. And each time the wave retains its displacement. After some time the wave will reach here. So the point A will be here, isn't it? So that point A will always retains its displacement. And this is possible only if the phase kx minus omega t is a constant. As the wave moves, both x and t are changing to keep kx minus omega t as constant. So, if the point A is to retain its displacement, what is the condition? Condition is kx minus omega t must be a constant. So, if kx minus omega t is a constant, then differentiate or the derivative of this kx minus omega t will be 0. And what is the differential? That means d by dt of kx minus omega t will be 0. Because if kx minus omega t is constant, then change of this kx minus omega t with respect to time will be 0. There won't be any change since it is a constant. Now differentiate this expression. Whenever you differentiate this expression, you will get, differentiate means apply this operator d by dt to kx first. That is the first term in this bracket. So when you differentiate kx, you can write k is a constant, then apply the differential operator to x. So you will get d by dt of x minus, then next term is omega t. So apply d by dt to omega t. So you will get omega into d by dt of t. That means dt by dt equal to 0. Here dt by dt is 1. So we will get k into dx by dt is equal to dx by dt is equal to or minus omega equal to 0. Right? Then take minus omega to RHS part. So we'll get k into dx by dt. This is x not n. Dx by dt equal to omega. Okay. And what is dx by dt? Dx by dt is the expression for velocity. Because x is displacement, dx by dt means displacement with respect to time. So that is velocity, linear velocity v. So we can write k into v is equal to omega. K into v equal to omega. Therefore velocity v is equal to omega by k. Okay, and you also know that k is the propagation constant and the expression for k is 2 pi by lambda. Propagation constant k is denoted by 2 pi by lambda. So substitute 2 pi by lambda here. So you will get, let me rub this 2 pi by lambda, otherwise I don't have enough space here. So k is 2 pi by lambda. So we can write omega by 2 pi by lambda. This lambda goes to numerator. So you will get equal to omega lambda. Again, omega can be rewritten as 2 pi nu, isn't it? Omega is 2 pi nu. Nu is the frequency. So 2 pi nu. Then here we have that lambda divided by 2 pi. Okay. So this 2 pi will be cancelled. So we are left with nu lambda. So we got an expression velocity v is equal to nu lambda. Okay. So what is the expression for velocity of a wave? Velocity v is equal to nu lambda. Very important expression. You must always remember this expression. In class 9 physics you had already studied this expression, but there was no any derivation based on this. So here in +1 course you need to study the derivation of this expression. So the velocity of the wave v is equal to nu lambda, where nu is the frequency of the wave and lambda is the wavelength of that wave. And next we can discuss about speed of transverse wave in a stretched string. So speed of transverse wave in a stretched string is given by this expression. Speed v is equal to square root of t by mu. You must remember all this expression. You must study this by heart. V is equal to square root of t by mu, where t is the tension produced in the string and mu is the linear mass density. That is mass per unit length. So T is the tension and mu is the linear mass density. So this is the velocity of the wave of a transverse wave produced in a stretched string, like the waves produced in a guitar, string, etc. like that. Okay. The next, speed of longitudinal wave in a stretched string. So speed of longitudinal wave means we can discuss about sound wave, because sound wave is a longitudinal wave. So speed of sound wave in a medium depends upon density of the medium, that means rho, and also one more thing, that is modulus of elasticity. Okay, modulus of elasticity, capital K. So the speed of sound wave depends upon two factors, density of the medium and modulus of elasticity. So suppose if sound waves are traveling through solids, because you know sound waves travel through solids, liquids and gases. So if sound wave is traveling through solid, then velocity of the wave v is equal to, yes, it is denoted by square root of y by rho, where rho is the density and y is the Young's modulus of that medium or of that solid. And suppose our sound wave is traveling through liquid, then in that case velocity is determined by using this equation B by rho. Okay, B by rho, where B is the bulk modulus of elasticity and rho is the density. And if sound wave is traveling in gas, that is the last medium, then velocity v is equal to square root of p by rho, where p is the pressure and rho is the density of the medium. And this formula is known as Newton's formula. Newton's formula. So Newton derived this formula thinking that sound waves propagate in the form of condensations and rarefactions, and these compressions and rarefactions are isothermal process. So we will study about isothermal process later. So according to Newton, this condensation and rarefactions or this compressions and rarefactions of sound waves were isothermal process. Hence modulus of elasticity is equal to pressure P. Okay, so whenever the sound waves travel through a medium, there was pressure variation. So he considered that variations as an isothermal process. But later it was found that this formula is not correct. It requires some modifications. So another scientist known as Laplace, okay, another scientist called Laplace, okay, Laplace, he corrected Newton's formula. According to him, compressions and rarefactions are adiabatic process. Adiabatic means there won't be any heat exchange. Isothermal process means temperature remains constant. Adiabatic means there won't be any heat exchange, okay, between the system and surroundings, and we will study more about adiabatic process in the coming sessions. I might have already learnt about adiabatic and isothermal process in your chemistry classes. So in such cases, we need to modify this expression like V is equal to square root of gamma P by rho, where gamma is the ratio of specific heat capacity at constant pressure and at constant volume. And we will discuss more about this in the chapter thermodynamics. Okay, so this is Newton's formula, V equal to square root of P by rho. And Newton derived this formula thinking compressions and rarefactions are isothermal process. But later another scientist called Laplace found out that this formula is not correct. It requires some modifications or corrections. That means this compressions and rarefactions are not isothermal process. These are adiabatic process. So accordingly, the formula is corrected like this. Velocity V equal to square root of gamma P by rho. Only the gamma factor was added to the Newton's expression. So this formula is known as Laplace formula. And this formula V is equal to square root of P by rho is known as Newton's formula. So that's about the speed of longitudinal wave in a different medium. So if sound is traveling in solids, it is square root of Y by rho. If it is traveling in liquid, it is square root of B by rho. And if it is traveling in gas, it is square root of gamma P by rho according to Laplace, but simply square root of P by rho for Newton. So that's all about wave and its terms, and also about the wave equation. Notes of the topic and YouTube video have been uploaded. Just go through it, and we will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.